Temperature is a measure of the extent to which molecules in a substance move around. Substances emit electromagnetic radiation depending on their temperature, to the fourth power. It follows the equation P over A equals epsilon times omicron times T to the fourth power, where P equals power, equals energy per unit time in watts, A equals area in meters squared, epsilon equals emissivity, which is the efficiency with which a substance emits electromagnetic radiation, and ranges from a value of 0, which is inefficient, to a value of 1, which is efficient. Omicron equals Stefan-Boltzmann constant, which is 5.67 times 10 to the minus 8 watts per meter squared per degrees Kelvin to the fourth power. At absolute 0 degrees Kelvin, which is equal to minus 273 degrees Celsius, molecular movement ceases, and so does electromagnetic radiation. For a less extreme example, take human beings. In the parlance of physics, we are all behaved nearly like perfect black bodies. That means that people are almost ideal radiators having an emissivity of 0.98. An average person has a surface area of about 2 meters squared, and naked skin has a temperature of about 32 degrees Celsius, or 305 degrees Kelvin. Therefore, the net electromagnetic radiation from a naked person in a 20-degree room is about 143 watts. So each of us is only slightly brighter than a 100-watt light bulb. Well, rest assured, you differ from a light bulb, at least in respect to your spectral qualities. The wavelength at which a substance emits the most electromagnetic radiation is inversely proportional to its temperature. It follows the equation lambda sum max equals 2.8978 times 10 to the minus third meters. A person with a skin temperature of 305 degrees Kelvin has a lambda sum max of 9.5 times 10 to the minus 6 meters of wavelength in the mid-infrared. For this reason, cameras sensitive to infrared radiation can capture the image of a person in the dark. The sun has an effective color temperature of 5,780 degrees Kelvin and emits a maximum amount of energy at 5.01 10 to the minus 7th meters, a wavelength that we perceive as the color of green. Over half of the electromagnetic radiation from the sun is in the wavelengths from 0.4 to 0.7 micrometers that are visible to the human eye. This is not happenstance. Not only do particle waves with these wavelengths have energy suitable to well-behaved biochemical reactions, but having an organ such as an eye that is most sensitive to the prevalent solar radiation serves surface dwellers like us very well. In contrast, cave dwellers have no need for a human eye because their natural habitat is devoid of solar wavelengths. Earth acts approximately like a black body with an effective temperature of about 287 degrees Kelvin or 14 degrees Celsius, and thereby emits a maximum amount of energy at 10.1 micrometers, a wavelength that falls in the mid-infrared. Several gases in the atmosphere absorb some of the wavelengths that Earth emits. In particular, carbon dioxide, methane, and nitrous oxide are considered greenhouse gases because they transmit the strongest wavelengths from the sun, from 0.3 to 1 micrometers, but they absorb major wavelengths emitted from the Earth from 2 to 8 micrometers. When gas molecules absorb infrared radiation, their vibrational energy increases, and so does their temperature. Warmer gas molecules emit electromagnetic radiation at shorter, more energetic wavelengths than cooler gas molecules. Putting this all together, a volume of gas molecules emits long-wave electromagnetic radiation proportional to its temperature. When illuminated with electromagnetic radiation of appropriate wavelengths, some of the molecules in the volume will absorb this energy and increase their movements. Through collisions of these molecules with their neighbors like a molecular mosh pit, movement of the volume as a whole increases. The gas volume therefore will increase in temperature and emit electromagnetic radiation at wavelengths that are shorter than the gas volume emitted before illumination, but longer than the incident radiation. Energy is conserved because the energy in the shorter wavelength electromagnetic radiation absorbed by a few molecules equals the total energy in the longer wave radiation emitted by many molecules. In summary, certain internal forcing factors, orogeny, eperogeny, and volcanism, depend on tectonic movements of Earth's crust. Albedo, the percentage of solar energy reflected, varies widely among different natural materials from 85 to 5%. Earth exchanges energy with its surrounding in the form of electromagnetic radiation. Number 4. electromagnetic radiation can be characterized by its wavelength. 5. Over half the electromagnetic radiation from the sun has wavelengths in the visible spectrum between 4 and 7 micrometers. Greenhouse gases in Earth's atmosphere are transparent to visible light but absorb in the infrared.